Hello and good evening. Welcome to another OWASP Melbourne chapter meetup, our very first meetup for the year. And well, it's already August. Thank you for joining us. We are so excited that you are here today. But first, before all of that, I'd like to begin by acknowledging the Wurundjeri and the Burn Wurrung people of the Kulin Nation, the traditional custodians of this land, and the Gawingal clan of the Darawal people. Sorry if I butchered that pronunciation. Of the land on which we are streaming from today, and pay my respects to their elders, past, present, and coming. I extend that respect to Aboriginal and Torres Strait Islanders people watching here today. So, welcome to the Meetup. We're still virtual. So, I mean, just really excited that we are getting back into the groove. Sorry for all the jank, and it's been a while. So, still finding my groove, our groove, getting things going. So, excuse us. Right. So, let's. Before we jump into the talk for this evening by Pedram, a couple of quick chapter updates. Let's just see if that works. Alrighty. Well, a couple of chapter updates. First up, if you have been following our Twitter, you'll notice that we announced a change of leadership. We'd like to thank Aaron for his generous service and help running the chapter with me the last couple of years during this pandemic. A couple of months ago, Gal decided generously offered to help step up and join the role as Aaron was stepping down. So I'd like to welcome Gal on board. She is Katniss Melb in Discord. Say hi to her. Well, the next thing is as we are ramping things up again, we are putting out a call for presentations. If you have a community-centric talk, again, no sales, no product pitches or anything of that sort. The goal here is to share knowledge and help people grow, help the community grow in its AppSec knowledge. We'll put for in the next couple of days, you'll see a couple of tweets from us about how you could go and submit your presentations. But additionally, we'd like to hear from you. We'd like to hear what else you'd like this community to be and what else you'd like us to do together. And it's not just about myself or Gal coming up and creating stuff, but what you can do with us and what we can do together to build this application security community and help us build better, more resilient, more secure applications together. So that's our call for suggestions. And last but not least, as I said, we are getting the ball rolling. So next meetup, save the date. Not much details yet. It'll be a panel on how to get into application security. It's on Thursday, 15th September 2022, 5:30 p.m. Just save the date. More details will come as we finalize and work towards the date. Yep. One of the things that you have noticed is that we also have a Discord. If you look at the bottom right of the screen, there's a Discord link there. Most of the conversations and the interaction will happen on Discord. Yes, I do see I have YouTube chat open, but most of the focus would be on Discord because we'd like to encourage that you hop in there, have that chat, and then past the stream, be able to still engage with the rest of the community, ask questions. There is a mention of in the meetup. We did mention that there is a CTF. That CTF will be open for about a week. So hop onto Discord, find your team, find other people, collaborate, and have a chat with. Towards the end, when we start talking about the CTF, we will be hopping into the Melbourne channel voice, chapter AU Melb voice channel, and basically just hanging out there after the main presentation is done. So yeah. Okay, I guess that's pretty much it for the main administrative stuff and updates. So without further ado, I have one more slide. So community news. Well, the big one is DEF CON 30 is happening next week. So if you are not aware, it's one of the largest InfoSec conferences in the world. Go check it out. there is an AppSec village there with heap tons of good AppSec talks. There is also B-Sides Melbourne on the 10th and 11th of September 2022, and OWASP AppSec Virtual APAC is happening on the 29th to the 1st of September, 29th of August to the 1st of September. So yeah, I think that's pretty much it. Yeah, so without further ado, I'd like to bring our speaker on stage. It will be a workshop. So we have Pedram, who would be speaking to us about an introduction to dApps security. Pedram is a security researcher who strives to close the knowledge gap among security and software practitioners. He has performed hundreds of security audits for Fortune 500, published over 25 zero days, reported thousands of security vulnerabilities, and led a global penetration testing team. His experience is backed by his strong academic qualifications and a PhD in information security. Sorry, I got distracted. Currently, Pedram has put his passion into building SecDeem, a boutique AppSec academy, where he and his team built the most accessible, comprehensive, and open training content for addressing security vulnerabilities in modern apps and dApps. Aside from SecDeem, he lectures an advanced cybersecurity master's course at UNSW for the Australian Defence Force Academy, and is founder of sectalks.org, the largest non-profit multinational technical security community. He has spoken at a number of top security conferences, namely HITB Netherlands, B-Sides, and AusCyber. His research on cloud security and honeypots have received global media coverage in the Register, Computer Security, and Insecure magazine. Without further ado, let me just switch and bring Pedram on board. One moment. Hello, Pedram. Yes, we're live now. Welcome. Yeah, please go ahead. Sorry, Pedram. Something weird happened. Could you say something again?
Yes, can you hear me?
Yeah, okay, now it works. I'm sorry. I think I accidentally hit the mute button.
Thank you. All right, you guys hear me? There's a bit of delay when I talk and when I see something in the chat.
Yeah, there is about a 15-second delay from from the time I hear you and the rest of the world hears you.
Okay. So maybe.
Yeah, sorry. So sorry. Please.
The question was, have you? Yeah, just get a show of +1s if you have used the smart contract. This helps me to gauge the content a little bit here. Yes. 2 yeses, I can see in the chat. Okay. If you can also bring up my presentation. We have received a few guesses, yeses, so I kind of assume the majority may have not heard about it, or this could be the first time. Now, let me start by talking about the app. Now, there is quite a lot of terminology today I may go through, so I will do my best to give a simple introduction to some of those. But so please hang on with me because it's a quite interesting one. So in general, the app is a decentralized app. Now, this app simply has two components. One is front end, the other side is back end, like the apps that we see in a non-smart contract world. The front end side, as you can imagine, is built using JavaScript. It's typically rendered in a web environment. The browser users, they can interact with it. The backend component is the part that will be run on what we see today, a blockchain, which is a whole new world. Now, since our focus is on security, from a threat modeling perspective, the front-end side of the app is effectively open to all the attack scenarios that you could typically find on a normal app, normal JavaScript-based app, the front-end based app. So all the type of security attacks that you may think about. But when it comes to the backends, the story is completely different. And as I'm assume majority of you perhaps in security or you're having some sort of security roles or you need to take care of it, this is the exciting part because we're gonna explore a new area. The reason being is that it is a scary word, this backend part. And just let me give you an idea. It's like a word that adversaries could have access to any source code, even the source code that is written by banks, enterprises, insurance companies, those type of codes that typically not find them online. You could access to that. They could download the code. They could run that code locally. And then here's the interesting part. They can test that code using real data. And these are the actual data that was previously used to run that code. They can test the code, then they can start finding the bugs, security vulns, and then they can proceed with writing an exploit for that type of a bug, that vulnerability that they have identified. When it comes to targeting the environment, the actual code, or targeting that place that they want to do, they can remain anonymous. It sounds scary. So with that, I actually want to welcome you to the world of smart contracts, because that's what it is about. If you have done penetration testing in the past or any incident response, most likely you have heard about a number of steps an adversary typically go through. Obviously, these steps are not written on the stone, but these are the ways for us to understand and try to classify the knowledge level or the extent of the attack, right? So here what I'm going to do is I want for us to get introduced to this whole new world, which from here on I may refer to as Web 3. I want to give you an analogy between Web 2, the non-smart contract world, and Web 3, the smart contract world. So as I talked about, reconnaissance, where an adversary tries to find a target in the smart contract world, is open source. They can download the code for anything. For initial access, well, they can access the attack. Probably going to happen in a normal Web 2 world against the prod instance of this thing that they're going to do. In the Web 3 world, they can run it locally, test it, and write exploit. So when it comes to evasion, that the techniques that attackers want to do to remain anonymous, in a non-smart contract world, they need to be quite careful. They need to have a quite solid OPSEC. Web 3, well, that's the design of the whole thing. You can remain anonymous. So as you can imagine, for an adversary, there is a huge ROI when they turn into Web3. And guess what? There is a lot of apps, well, the programs that are written for this Web3 world are dealing with the financial data or semi-financial data. So it's quite lucrative to look into it. So let me start by introducing a number of terminology that you may have heard, and I'm going to use it throughout the rest of this workshop. It's effectively our crash course. One is, what is a smart contract? A smart contract is effectively as a program, but this program does not run on our a normal system or Web2 system. It runs on a different machine, and this machine is referred to as an Ethereum virtual machine. Now, these days we have different virtual machines as well, but for now, let's just focus on this single machine. Ethereum. Now, for now, let's forget about the cryptocurrency that is also named after Ethereum. Ethereum, in our context of what we are going to talk today, is most likely you have heard about Bitcoin, is a Bitcoin plus an state machine. And anytime we hear about a state machine, that means that it's a system, it's a machine that you can write code for, and this machine can do stuff. The name of that machine, that state machine, is simply referred to as EVM or Ethereum Virtual Machine. This is a machine that runs the smart contract, those programs. Now, the difference between these machines and the normal machine is that it runs on a distributed network. So it has different rules comparing with the normal VM that we may run on our host. Now, what is the distributed network? Well, that is blockchain. Now, this blockchain, this network, think about it as like a distributed network. There are multiple EVMs are connected to this network, and they communicate with each other. They send information, the data, they deploy stuff. And there are rules, or let's put it, rules of the game for each of these EVMs to introduce something to this network or to put something on this network. Similar to any type of distributed network, well, blockchain networks are different, and obviously there are some safety and security things designed in it. You may also hear about the term node. So effectively, a node is a machine that runs EVM. So far, so good. I'm still having all of you guys here. By the way, Dan or anyone on the chat, if you guys want to stop me, just feel free to do so.
Yep.
And finally, Solidity. Solidity, as I said, we are writing a different program, which is known as a smart contract. And like any other programming languages out there, Solidity is a language, a popular language that is used currently to build smart contracts. Do we have any other languages? Yes, we do have. Solidity currently got the popularity, which some may say is one of the worst language perhaps is developed. I'm not gonna get into that, but it's very similar to, if you may say, it's similar syntax to the JavaScript. Moving on. Let me give you a more analogy so that we get more familiar with these smart contracts. So, smart contracts versus a typical web app. When it comes to the execution, any program that we run, it boils down to bytecodes. And those bytecodes are effectively the things that the CPU will understand and will execute. This is similar in the smart contract board. The EVM effectively runs bytecodes. Obviously, we have some assemblers similar to the non-smart contract world that we can see what these bytecodes or these machine codes are, so we can easily understand them. The reason I'm saying it, because today we're going to see some of those. So it's effectively that. Now here the parts, perhaps this is the most similar part out of all. Here is the thing that things gonna change. When you have a web app, when you wanna send a request to it, effectively you have a web app, let's say talking about the banking portal, and then I will go there and want to transfer money from one account to another account. And this would be commonly used the HTTP protocol. You will log in, you will choose an account, and this request will be obviously through the TLS secure. Now, if I have the same type of app in the Web3 or written in a smart contract, this story is completely different. Now, again, the same app that I can transfer a fund from an account to another account, but I can't just say directly send a request to it like the way that HTTP request is. The way it works is like it's like a massive room or massive like big room that a lot of people are listening that, and I will broadcast that, hey, I want to transfer this amount from this account to that account. Can someone help me? So it's a public message call. And that is also referred as a transactions. It's not like a point-to-point IP-to-IP type request. It's more like you send a message in this distributed network and someone will pick it up. Now, the other very interesting part is the response. And these are the things sometimes I say to people that when it comes to the smart contracts or Web3, we need to relearn a lot of things because some of them is quite different from our non-smart contract world. So if you are used to either write a code or do a security audit in Web 2, you may find it a bit complex when it comes to Web 3 because the rules of the game are very different. So we may be used to trying to invoke an edge case scenario that always happen in a Web 2, but Web 3, that doesn't happen. But we have all sort of different type of edge cases that can go wrong. Response. I send a request, transfer this money from this and that, and I'm going to get response back, HTTP 200 or HTTP 400, right? Smart contract world, the responses are not instant. So it means that when I send a request, I broadcast that request, then I need to wait for one of these nodes or EVMs to pick up that request and process it. This is the concept of mining. So it will take the request, it needs to do some calculation on that, and then once it finds the response, it needs to put the response back to that network, the concept of mining. Now, I'm not getting into the detail of that. And once that happens, that response, obviously I can read that response, it's not final. It means that at any point in time, not at any, but at some point in time, this response may get canceled, may get reverted due to a number of reasons. So I need to still wait for a couple of more minutes, and in some of the distributed networks, maybe an hour, for this response to eventually become final, like 99% final. So what I mean by that means you transfer money from one account to another account, and you get the initial pass response that, okay, this would be the result, yet the transaction is successful. But then again, there need to be, you need to still wait for more calculation, more mining to be done for other transactions in the network to make sure that your response or your request is always stays in the distributed network. Now, if I talk about time, at the time when I was preparing this workshop, it was around 1 hour, almost 1 hour for a Bitcoin network, those popular distributed networks, and all for the Ethereum was around a couple of minutes for a response to get finality or 99% final. Now, finally, most likely you have heard about, if you are a dev, the concept of mutability and immutability. Mutable is the things that can change. Immutable is the things that cannot change. Constant versus variable. Now, in the Web2 world, we write the app, we push it, suddenly someone will find a bug. We go, oh, holy crap, we need to go and patch it. We push the code changes and deploy it, yada, yada, yada. In a smart contract world, well, the code is immutable. Once you deploy it, that's it. Like, you can't change it. And perhaps that is the end of my workshop here, because if you happen to write a code that is vulnerable to some sort of attack, that code will stay in the network, well, and you can't change that. It's gonna stay there, buggy, and potentially people are gonna come and exploiting it. But obviously, if that was the end of my presentation, I would not have the rest of the slides here. The story is different. Yes, the smart contracts are immutable. You can't change them. There are some programming design patterns that engineers, they follow to also update that, in a sense that one of them, for example, is they create a proxy contract that this proxy contract always try to refer to reference to a latest version of a contract. So say a contract was deployed and there was a bug, they want to patch that code, effectively they deploy a new version of contract. So that one stays in the network, they deploy a new one, and they use the proxy to send all the users to the new program. So far, following me, shall I go deeper than this, or shall I stop here? One more. All right, let's go one layer also deeper. What's the difference between EVM and a 64-bit machine? Maybe the laptop or a MacBook. Well, not the M1 MacBooks, but the Intel-based MacBooks. So what are the differences there? And if you have done some computer science degrees in the past, or most likely you have some buffer overflow exploitation, most likely you have heard about registers. So when it comes to the 64-bit machine, we have these registers, and registers are these tiny memories of the CPU that CPU uses for the calculation, arithmetic, and a lot of things that it needs to do. In a 64-bit machine, we have 16 registers. In EVM, we don't even have a register. Both of them are stack-based machines. So a stack, if you remember, when we put things on the stack, the last thing you put on the stack is the first thing that you take it out. Storage, so in a 64-bit machine, I may store all the program, the code on my machine, but when it comes to the EVM, the code, the storage is effectively persistent on all the nodes, all the full nodes, or the nodes that are on the network. Again, I didn't go through the detail of what are different types of nodes are, but effectively the program or that smart contract are persistent there. When it comes to the execution in a 64-bit machine happens on my CPU and I run the program here, but in EVM, we have these miners, or again, the nodes that will process those requests in a distributed way. And two last things we need to remember, the most of them is the word size, the size of that stack. Well, in the 64-bit machine, of course, is 64-bit, but in EVM is 256-bit, and we will see why that is matter later. All right, so if you're still following on, perhaps you're gonna ask me, all right, let's just get rid of these and tell me where to look for vulnerabilities. Where can I find the bugs in this system? Well, the stack is quite big, and you can choose to look at any of these effectively layers that you can see here. Now, the layer 0 is the front-end part, which is written in the JavaScript in a dApp, for a dApp. But the one that we're gonna look at today are these 5 other layers. So a smart contract, this is the code written by any developer out there. The compiler, in this case Solidity, that use and take that like a normal word, right? They take that smart contract and gives us the machine code or the bytecode that will be run on the EVM. Any EVM implementation, so this one like Geth is like a Go-based implementation of that. So if there is any vulnerability there that could perhaps impact the whole network, or any other protocols that is used in this ecosystem. So I talked about rules of the game. So if these EVMs, they want to put something on a network, well, there are some rules they need to follow. There is a hashing algorithm. There is a protocols of proof of work, proof of a stack. Yeah. Imagine if, for example, it's like if someone find a bug in TLS, and that will impact all the implementation of the TLS using that version. And if you are curious, the hashing algorithm at the moment is being used is known as key check. This one at the end is like a SHA-256. And finally, that network itself. So it's an Ethereum network, it's a layer 1 network, layer 2 network. Again, it's just so exciting. So many things that you can explore that. For now, for this workshop, I'm gonna only focus on the first layer, a smart contract, because that is where perhaps the most of the mistakes we're gonna see. Okay. Now let's talk about from here on, I'm gonna start with talking about an incident and then eventually introduce you with one security bug, vulnerability. Then we're gonna talk about, we're gonna see a demo that why this vulnerability happened in the programs. And then we will talk about a couple of ways that we can go and fix this bug. Once we're done with this, then we're gonna move to the CTL. We're actually gonna do this in practice. Now, starting with an incident. Again, any questions or things so far? Anything, Dan?
Nope, not really seeing anything come in. Chat, any questions? Everyone still following? I know my mind's a bit exploding right now, but lots to learn here. Lots to learn.
Is there any part that I need to be a bit more detailed, or maybe one more?
I think it'll take my brain a bit to digest. This is my first contact with all of this, so yeah, lots to learn.
I hope I'm not losing people now.
Yeah. Hopefully I can make some intelligent questions following up while my brain starts trying to digest a bit about all of this. Yeah.
All right, let's continue.
Yeah.
Okay, this is one of the many incidents that happen in the smart contract world. As you could discuss, as I started this conversation, the ROI is high. So effectively, well, there's many people will target these programs that may not be written so well. And anytime you deal with financial data, that target become even more lucrative. Hence, we have so many incidents that happen in this world. One of which was related to a contract known as Beauty Coin. And this incident happened in April 2018 that someone stole this amount in 2 transactions by exploiting a vulnerability in the contract for Beauty Coin. Now, obviously, there is no one-to-one mapping of this number to a dollar value, but even if it is not, even if it is like a couple of cents, this number is huge. So hence the incentive to do that. What was the issue? Well, the issue was in a single function, and the beauty of this system is now we can, as a security professionals or someone who is curious, you can actually go and see what actually happened, what was wrong. You don't need to wait for the statement of that enterprise to tell you about the incident. You can actually go and download the code, look at that function, but guess what? You can even see the data that attacker used to trigger the vulnerability there. And that is, for me, this is very educational part of the thing. So you look at the batch transfer, there was a batch transfer function, and this function was getting a value from untrusted source. It was using some arithmetic on that, and eventually that will do some weird cases, which I will talk about it later. Now, just to tell you that this was a source code related to that, you could go and have a look. The value was coming from as an argument. This is effectively perhaps the first view to a smart contract world. So this is a function. As you can see, this function will receive a number of arguments. So it receives an array following with a value, and it will also returns a return value of Boolean. So easy to read, and it does some operation on it. But if you look closely, there is a arithmetic done right at this line. And here, what we kind of see here, these are all the data types for these variables. And as you can see, we are getting this thing called value, which comes from an argument, and this could feed from an untrusted source, so it means that user would be able to supply that. We are just multiplying that to this counter value. And bad things can happen, right? Because these things can go beyond the range of this data type. And this is where the integer overflow happen. Now, one thing is, anytime you see u next to int, it's unsigned integer, meaning that we don't have negative value. We're starting from 0 all the way to positive. So this value, once it goes beyond the range of u in 256, the overflow happens. So suddenly the number wraps around, and that caused this whole code to effectively act weirdly, and eventually the sender will receive all the money that was stored in this contract. Whoever perhaps stored the money in this contract, they would be able to receive it. So it is a bit, as a security professional who has been in this field for a while now, it's a bit disheartening to me to see this type of coding pattern, like things like that. But more than that is that why on earth we have this integer overflow problem on a virtual machine, which is known as EVM, which is built effectively, the white paper was around in 2015. Integer overflow, I think, is a kind of a vulnerability that maybe is older than my dad. It existed since the beginning of, I don't know, calculators. So it's disheartening for me because we still see this problem here. Now, obviously, we are dealing with a virtual machine here. We didn't have those restrictions of the hardware and the CPU registers. So why we even have this problem? Now, I don't know, maybe it's because we haven't really learned the mechanism of how the numbers are being stored on a system, or maybe a little bit lower level that what actually happens on a CPU when we add or remove or multiply two numbers. And that's why I want to take a few steps back and talk a little bit about why in the earth we even have integer overflow, now let alone in the EVM. And hopefully for the people who are now watching this workshop, and if you in future, if you're gonna build a new virtual machine or a state machine or a framework, hopefully we are not gonna see this problem anymore. Now, obviously, there are some restrictions we have in terms of hardware, but the things I'm gonna go through, you will find that actually it was quite an easy fix that we could not even have it in the EVM letter, so those contracts will not even get exploited in this way. So now Web 3, put it aside, let's come back to Web 2. Computers effectively are giant calculators, and if that's what originally they were built for, and these giant calculators, they will have a CPU, and this CPU have that tiny memory cells on it, which is called registers. And why we do have those registers is because when the CPU wants to do the calculation, the numbers will be fetched from the memory, put on those registers, and then the arithmetic will happen and the result will be pushed back to the register. And this is quite fast, it is quite performant. Hence, this is the architecture of the majority of the micro architecture. This is the concept they go through. Now, as I said, these registers are limited in the size. So you may have a guess that if you have a CPU for a 32-bit system, the size of this register is effectively is referring to the size of this register. So a 32-bit system can represent a number, but it has 32-bit to store a value. For a 64-bit machine, which the majority of the machines today, has 64-bit available to store any number, which is equivalent of this maximum number. So in a 32-bit system, the maximum number, now forget about negative numbers for a while, is this, is number 4 with 9 digits in front of it. And a 64-bit is way bigger. Okay, so just remember these two numbers again. So for a 32-bit, we have 4 following with 9 digits. Now, having that in mind, let's say we have this pseudocode from a language called Java, and we have these 3 variables. We have a variable called surcharge with a value of 1, 2, 3, 4. We have a value called fee with variable called fee with the value of 2 and 9 digits, and we have a value called total fee plus surcharge. So what would you think would be result of this transaction? So which will be done on this total fee? What the program will respond, you think? And anything comes to your mind, please shout it out. Are you guys following? Any thoughts? What's gonna happen here when I add this to this? So this effectively to that.
Nothing happens. It just adds up, I guess.
It just adds up. Yes. Would that add up in a way that we expect? Anyone on the chat? Would we get just a simple addition? Would our program will give us a weird number, or would our program crashes?
What does chat think?
Overflow the number. We are getting close. So what would that mean, like in other sense? So we kind of be referring to that we get a weird number, but what would that mean? Like what? Yes, Grandmaster. Yep. Pretty close. Yes, we're gonna get a big negative number. And you know what? If you have reviewed some of the classic code for the financial systems, minus in some of those systems means a refund. So effectively, once this calculation happened, once this thing was added to this, you're gonna get this massive negative number suddenly. And guess what? Once we want to do a perform transaction on it, rather than we charge something, we may refund that person. I personally come across with this issue on a number of systems, that a negative number suddenly refunded the person rather than charging them. Now, but one question, and I want to see if you have paying close attention to my slides. Remember, I mentioned that on a 32-bit system, the biggest number that we can store is 4 with 9 digits. Here I have 2 with 9 digits. So what caused this become negative?
Would it be, I don't know, sounds like maybe it's a 16-bit system?
I mean, it is a good thinking, right? Effectively, we want to store both negative and positive numbers, right? So although the biggest value we can store is this range is divided in half. And when it's divided in half, that means, yes, we have some good computer science people there. The first bit is normally used to store whether this number is positive or negative. Perfect. Hence, that problem happens. But there's a few things that still to go through. So to do any integer calculation, well, integers like that number that you guys see, we have a fixed amount of bits available to perform the calculation. On a 32-bit system, the first bit to represent is used to represent whether this number is positive or negative. This is known as a signed bit, simple. And that means the range that we can play with is this. But the other question here comes in that, so if I have this number, if I add 1 to it, why this suddenly turn to negative? Like, why in S we have this kind of effectively weird behavior that once we add a single bit to a thing that covering the whole range up, why it becomes like that? Well, This is to do with another thing, perhaps not many people pay attention, is to do with modulus arithmetic. And this is the why we're having it on a CPU, I don't know, but processors implement modular arithmetic anytime they deal with, well, arithmetics. So what is modulus arithmetic? I don't want to make it, it's super simple to know. Is effectively, we are doing it in our daily life. Well, I'm doing it. Anytime I go to a doctor, then she prescribes a medicine for me to take it every 4 hours. If now is 9 p.m., which I take the medicine, so I know immediately the next time that I should take this medicine, it's pretty late at night, which is 1 a.m. So effectively, I use modulus arithmetic in my brain. How? Well, 9 p.m. is 21 plus 4 equals to 25. Now overflow happens in my brain. 25 obviously doesn't exist in our system. 25 divided by 24, I will take the remainder 1, and that is 1 a.m. There you go. This is modulus arithmetic. So you may notice here that it makes sense to use modulus arithmetic in the context of time. Now, it may not make sense to use modulus arithmetic in a different context. Now, I leave this as a questions to ask people with more hardware background. Obviously, there has been some reason that we use modulus arithmetic when it comes to microprocessors as well. So this is what happens effectively in our CPU. This number from that pseudocode plus this number is equal to that. And that's effectively what I will do if I wanted to add it up. But this number is bigger than 2 power 32. So there are not enough bits available on the system to represent this number. So what the microprocessor will do, will effectively divide that by 2 power 32, 31, and we're gonna get this result back. And this thing, again, I don't wanna make it hard, this is actually equivalent of this negative number. So coming back, hopefully we understood what's going on. Is we have 2 problems here. We are using a fixed size data type to store something, and once to store a number, and we don't perform any range check that if this number that we are storing is beyond that range or below that range. And since we have this default behavior in our microprocessors, this number will wrap around anytime you add something to it that goes beyond the range. And hence we have the notorious integer overflow. This is when we do arithmetic operations, and this arithmetic operation results in a numeric value that is outside that data type that we use to represent. So we use int32 to add 2 numbers, and these 2 numbers could be bigger than int32. It also happens in integer overflow when we do assignments. That means that we have a number that is in a 64-bit format, like it's as big as a 64-bit, and then we want to cast it, assign it to a 32-bit data type. That is also where overflow happens, and this value will wrap around, and suddenly a positive number becomes negative, and negative could become positive. So what are for those of you who are more on engineering side or doing code review, these are effectively edge cases that we will be looking at to find out if the code is vulnerable to integer overflow. There are around 22 edge cases. These are the 22 places that we need to have this is a bit of a joke, we need to have more like a grown-up software engineer to be careful when they do the calculation anytime they use it in a smart contract board. Pluses, minuses, divisions, and things like that. Not only those things, we also have, if there is any bitwise operation, like a left bit specifically, we're gonna have this problem, integer overflow. And finally, the assignment. So here I have an int 256, and I cast it to int 32, I'm gonna get an overflow as well. Now, all these problems happen because of the limited amount of space we have on the registers. And we also use modulus arithmetic when we come across with a value which is beyond the range of that register. Now, here is a question. Maybe some of you are going to ask me that, hey, wait a minute. When at beginning you introduced EVM to us, and you compare that EVM with the x64 machine, you mentioned there is no registers in EVM. Like we don't even have registers in this system. So why on earth the number will wrap around? We don't have limitation on EVM because we don't even use registers to do any calculation. It's a virtual machine. Did I lie, or what was the problem? Any thoughts?
Not sure about this one. I'm guessing
Design flow, no overflow exception. It's a good point, but why we even have this problem that we need to even have exception for it? Compiler implementation. Getting close. I'm referring actually to EVM itself. It's like one layer below compiler. But yeah, is it Ilya? Yeah, Ilya is gonna be interesting one because that's where the problem gonna. JVM was a stack base as well. Perfect. Yep. A virtual machine needs to talk to the hardware effectively. That is also correct. But you know, one thing I didn't talk here was, well, we don't really have overflow problem for languages such as JavaScript or Python or Ruby. As you said, it's being eventually gonna run on a hardware, but those languages, they use different techniques to manage these effectively big numbers, right? So why we don't have it on EVM, especially in a virtual machine, well, we don't really have a register. Now, this is a part that got me interesting to just figure out what is going on, like why this problem happened. And as many other security professionals here will do, well, you do reverse engineering. And that's got me to do. And the first thing we need to do for reverse engineering is to find a debugger to gives us an overview behind the scene that once I have a contract and that contract will eventually get boiled down to the bytecode, what is gonna look like on the EVM so I can track it and find out where this overflow happened. You guys ready for a ride? We go a little bit lower level and figure out what actually happened. Yeah, Dan? You guys ready? I stop sharing this.
Yep. Let's go.
I share my another tab.
Yep.
So, okay, let me see which one of tab is this one. All right. So what I'm going to do now, we're gonna go even more lower, but this just stay with me on this one. This would be fun. Explore. All right, this one. So, well, I wanted to look for a debugger, but turned out to be there is no debugger that can gives me that level of detail that I want. Well, there are some effort to kind of have a plugin for a Radar 2 or R2 or GDB, but unfortunately, when I try to run them, they all get segmentation fault. But what happened was I actually found something very interesting. There is an IDE called Remix, and if you guys want to play around with it, it's online. So you effectively search for Remix IDE, and if you have done or if you have heard someone want to start doing a smart contract, they will normally write their hello world Solidity or smart contract using this IDE. But I'm gonna use this IDE to debug integer overflow. Because this IDE, although is web-based, maybe it sounds a bit counterintuitive, it does have a debugger that relatively give me the details that I'm after. So you can simply open it up. And what I'm going to do here, what I've done was right on the left. So I will give you a bit of introduction of what is this. So here where you got all the program code or the contracts. If you want to write test, you put it on this directory, and you can also run some script against your contract. That's all good. So I'm gonna create a new contract here, which I've already done. So what I've done was I created on this plus button here. It will ask me, not this plus button here, this button here. It asks me to create a new file, and I have already created a new file called overflow.sol, and I pasted this code in it. Now, what does this code does? It's let's just ignore this part for now. Let's just focus on this function here called arithmetic. It takes two numbers, a and b, both into 56, and it will add it up and return. Just a touch of the water, just to see, do we have any functional programmer in the room? Do you know what is pure? If no, you please post it on the chat. Anyway, so this number takes two things and will return it back. I also have another function called unsigned arithmetic. It takes, again, two numbers, a and b, and it calculates, it adds them together and returns it. But these two numbers need to be unsigned, meaning that the minimum value will be 0. We can't really represent minus there. And that's it. So let's just focus now here. Now, what things I have on the top, if you done, any programming before, like normally you start with a thing called class, but in a smart contract world, we start with a thing called contract in Solidity. And here is a convention that we need to put licensing on the top. Otherwise, the compiler will not compile our code. And this is Pragma Solidity. This is where we specify what version of the compiler we want to use to compile this code, this contract. Here I have specified anything after this version, before this version. Now, one last thing, these things here I put here, these are just helper for me because I'm going to do some calculation based on maximum representative value of integer 256, uint 256. I effectively, rather than Google it, I just get it here, so I just can pass it around. All right, so we have this contract. Now I'm going to move to the left. There's this icon you can see here. This is a Solidity icon. Here, right in the IDE, I can pick a compiler to compile this code for me. So hit on this thing here. Let's scroll down. For now, we're going to use the compiler versions 0, 6, and 10. Select that. Now it will go and fetch that compiler, all written in JavaScript. When you hit compile, and this is the name of my file, overflow.sol, it will compile the code. No issue found. Perfect. Now, I compiled the code. Now I need to effectively run this code. But before, as I said, the rules of the game here is different. To be able to run a smart contract code, we need to deploy it on a network or on a blockchain. And again, we can do all these things in this IDE. If you head to here, deploy and run this icon here. Again, in the browser, I already have a mocked blockchain or a testnet. And here you can just simply press deploy. This is effectively now deployed that machine code to the network. Now I can start interacting with it. And right at the bottom here, deployed contracts. These are the contracts that are currently deployed. They are in a cloud, we can use them. There we go. Now the UI is not very intuitive, but it's powerful. It gives us a lot of things when you want to build something or debug something. Now, firstly, what I do, these are my functions. You can see they follow the function names that I have here. So store, arithmetic, and then this one, unsigned arithmetic. You can see unsigned arithmetic here. Now, the first thing I want to do is I want to just find out what are the maximum value for these data types. So I hit store. It does a calculation. Now, if I press on these are, you see, it maps to the variables. So max signed, max unsigned, mean signed, and mean unsigned. So this number that we can see here now is the maximum number that's signed in 256 can store. And this number, which is a lot larger, is a maximum number that you in 256 can store. Okay. Now let's just do a simple arithmetic. So just come down next to unsigned arithmetic, and let's say I want to add two numbers. My number A would be 1 and B would be 2. So 1, comma 2. And you press unsigned arithmetic, and there we go. We got the result back, u in 3 as expected. But now we want to see what actually happened behind the scene. You may have noticed every time I did some operation here, there was something printed out here. This is our effectively the output of the transactions that I'm doing. Now there is a button next to them called debug. Once you press on that, it will open up our, well, relatively detailed low-level debugger that I was after to figure out what is going on with integer overflow. Like many debugger, you have a step into, a step back, a step over, things like that here. Now, the way that the debugger works, again, this is another thing we need to learn, is that we don't really set a breakpoint and then we run the program and it hits the breakpoint. It's more like looking back in the history for the execution that was done. So we debug the transaction or the things that we have done in the past by doing so. So what I'm going to see in this view is the first thing is this part that I'm very interested. This is my execution stack. So these are the execution that will be happening on that machine. And let me maybe zoom a bit. So it's effectively the machine code now being disassembled, so I can read the what is going to happen. So that is one thing is very interesting for me to go through. The other thing is this guy stack, and this is the stack of that machine. Now we can ignore the rest. We don't want to worry about them. So I got the stack and I got the things that will be executed. Now when I hit the debug, it effectively came back to the point where I provided those two values, 1 and 2. As I said, in EVM, we don't have any registers, so everything is on the stack. What I have on the stack, when I enter this arithmetic function, the leftmost value, which was B, is 2. You can see it here. It's on the top of the stack, position 0, and value 1 is right below it, 1. The instruction that will be executed is push. Now, we know every time push happens, a value that follows it will go on top of the stack. By the way, anyone here has done debugging or on an x64 or x32-bit system? Just shout out in the chat. All right, so let us step into. I don't need to worry about a lot of these things. I just come all the way down here. So as you can see, push executed and 0, 0 is now on top of the stack. Now there are two instructions could be new to us because we don't really have them in the 64-bit system. Now this instruction is called duplicate. So duplicate following with the value 2. So that is effectively take the second value on the stack and put it on top of the stack. So let's just this to happen. So you can see number 2 came over on top of the stack. Now duplicate 4, similar, it will copy the value which is in the position 4 of the stack, 1, 2, 3, 4, and put it on the top of the stack. So these two instructions were executed to prepare the stack for this instruction, add. Well, what add gonna do? Simple, just gonna add two numbers. And the way that add works, it just looks at top of the stack. It will take the two value of the top of the stack and then it stores the result back on the stack. So here I should expect now what's going to happen is, let me enter it. Here sometimes I lose this. I need to see 3 coming on top of the stack. There we go. Simple. We can just ignore the remaining instructions, swap and pops. So, and all the way, we're going to see a return instruction, which kind of returns back to our main program. And hence we got 3. So many things just to add 2 numbers. So now let's do something more interesting. Let's just go back to our deployed contract. And this time I'm going to do unsigned arithmetic. I'm going to take the maximum unsigned arithmetic, this value. It's going to be my first argument. And the second argument will be 1. So now we're going to investigate. So what we think is, so this massive number, effectively, if I add 1 to it, what's going to happen? Let's see. 0. We know that overflow happened. And suddenly the number wrapped around, and since I'm dealing with the unsigned arithmetic, it becomes 0. Now, if I deal with signed arithmetics, if I take this and use my signed arithmetic thing here, like this number, plus 1, this should give me a negative number. You can see negative whatever it is. Now let's go back here. Let's just do this unsigned arithmetic and let's debug it. Why overflow happens? This is the moment that things getting interesting. Again, I'm coming down here. What we have on top of the stack, I got 1, and the second value, sorry, the first value, the rightmost value 1, and the left value is this number. Now we need to say this f. How many times? This is around 64 times f, which is equivalent of all the bits used for 256 unsigned. So what will happen now? Again, the first instruction I have, push 0, 0. It effectively empty top of the stack. So 0 is now on top of the stack. The second thing is duplicate 2. So this is going to take 1 and put it on top of the stack. There we go. And then duplicate 4. There we go. Now let's just say f for 64 times, because now the add going to happen. There we go. And suddenly things turn 0. Why? Because although in EVM we don't have registers, but guess what? The stack is limited to 256 bits or 64 f. And hence when I add something there, well, the decision is, well, let's wrap the number around. Yeah, you may ask, could we just throw an exception? I think there was things in chat. I think, yes, we could. Well, for some reason, that was not a decision in the EVM system to throw an exception that, hey, these things that you are adding to this f goes beyond the range. So rather than trying to be, well, in this case, wrap the number around, you just could tell something. Well, that apparently didn't happen. And hence, we are dealing with integer overflow on a system where it is pretty new, as new as 2015. And there we go, all the way down, and we got the 0 out. All right, any questions so far? Any part that you guys want me to explain a little bit more? If not, we continue talk about a little bit about things that we can do to fix this problem. Can I get a show of hand or a plus ones that how many people are still following this? I hope I haven't lost you guys. I know I'm going through a lot of FFFFF and assembly code at, I don't know, it's like 7 p.m. now.
Beer o'clock. Yeah.
Yes.
Well,
Grandmaster. Well, I kind of agree with you. Yeah. It's just, maybe let's put it this way. It was nothing priority on their list. to take care of when EVM was being considered in the design of the EVM. There's actually a white paper, a theoretical white paper behind it, but the implementation, well, this is what it is. So yeah, and you're gonna see the interesting part coming in, that what was done to try to fix it up. So, well, yeah, we have limited stack and we have simulated. I don't know whether this is a default behavior or it's because they wrap around, but well, it happens. For me, it's more like the message, maybe the understanding or the awareness was not shared across to whoever was designing this. Can the unit test? Exactly. Yes, we can do unit tests to fix these things up. And in fact, Eric, we do even have interesting fuzzers that we can use in the smart contract board to fuzz and potentially find this security bug. Integer overflow is quite interesting because it is I would say it is the only vulnerability that is similar to Web 2. So it's for us to get into the security side of Solidity. It's an interesting start because we know integer overflow happens in Java, in C#, in C, C++. So it's kind of the same concept. So it's very easy for us to get into this. Correct, yeah. It's a virtual machine anyway, so why the performance should be an issue here that we could just throw an exception. Now, let's just talk a little bit about, let me go back to my slide. Let's just talk a little bit about, well, what can we do to fix this? Like anyone on the chat, how would you go after fixing this problem?
Do boundary checks?
Do boundary checks, yes. I'm glad you didn't just say validation. You've been very specific of what to do. That's great. That's great.
I mean, you did give the answer a few slides back, so
Yeah.
paying attention.
Yes, I will definitely share some info on that for the resources. Okay, so obviously, when it comes to, as I said, this is an ancient bug. So we did learn it in a hard way, how to deal with it in the other languages, and same applies here. It's nothing different. So how do we address this problem in the code is we talking about three strategies, or I call them defensive programming strategies. One is obviously, as Dan mentioned it, is around range check or specifically precondition check. So before we do any arithmetic operation, we will first check that if this operation will result into an overflow or underflow. By the way, underflow is also an overflow, just it happens on a negative range. And if so, we don't do it or throw an error or call an exception. And the other technique is known as upcasting. So effectively means if I want to add two numbers which are in 32-bit range, I use a 64-bit container or variable to add these two numbers, and then I will effectively not going to go overflow. But the problem of this approach also, as you may imagine, is what if the number is bigger than 64 range? Maybe I'm multiplying two 32-bit values, maybe that goes beyond that other type that I have selected. And the third strategy is usage of the dynamically allocated data types. These are the data types that will use effectively the memory to store that value. So the memory is theoretically the limit for these data types. Now, if you have done some programming in Java or even in JavaScript, we do have it. There's a some data types known as big integer, big int. These are the data types that are backed by a memory. Now, performance-wise, they are horrible. Horrible in the sense that since they are stored on a memory and all the arithmetic things need to be a callback, a return call to the memory, is not as performant as an int, but it will definitely save us for, well, a huge value like 256-bit value. The problem of these three strategies, or this last strategy, is that we don't necessarily have this implementation in EVM. Where if this was a workshop for some of my workshops on like Java or C#, I would definitely recommend anyone to, hey, go with the option number 3. You're safer there. I don't think the performance gonna hit you as much, but you are safe in a number of cases. So don't try to use int. You'll just use this dynamically allocated data type. But unfortunately, we can't really use that in a smart contract world. So we are limited with these two. So effectively what that means is if I want to add two number, let's call this a safe add, which will take A and B. So what I need to do is I need to do a check. I can simply add these two number and then we'll check that if the result, this is just this case, is less than one of those values that was passed in, right? So that means an overflow happens. So if I add a massive A, maximum U in 256A with a 1, the result will be 0, and 0 is less than 1, so that value, so that means that an overflow happened. So we can follow with a similar now concept going forward. I think I needed to, let me go back to that Ethereum. That IDE. Let's just, for example, have a look at one of those techniques. Now, before I want to continue here, one thing I want to mention was that I used this problem of integer overflow was quite large, and given the number of incidents that happened to the smart contracts, the whole Solidity community came around that, hey, we have to do something about this. And then what happened was that they decided to, at some point, they decided to fix this problem within the compiler. I think Ilya was mentioning in the chat whether that can be done. And that was actually the case. So what happened now is from this version of the Solidity, so if you look at my IDE from version, let me just double check it.
Padram, I think the screen stopped streaming. Can you check your screen share again? Sure. Yeah.
So do you see now this? Yeah, I think it's showing up now. Do you see my mouse moving?
Can you try stopping the screen share and starting it again? Because I noticed the screen share dropped. Yeah, sorry for the jank.
No, I think it's
technology's hard.
Let me check. Why there are two of them here? All right. There we go. Go back. So from Solidity version 8, the compiler does inject additional instructions anytime it sees an arithmetic is being done. Effectively, the compiler will inject a number of precondition check to the code and will kind of throw an exception if that value gonna go beyond the range of that data type. So let's just see in this practice, and this was also gonna lead to an interesting discovery here for us. So I'm gonna now move back. Let's just say I use the version 8 of this Solidity, and let's just recompile my contract, go back to the deployment, and right here, let me close, minimize this, and I need to deploy it again. This is compiled using the version 8 of the Solidity. So this is my old contract compiled with version 6.10. This is a contract compiled with version 8. Now, let me also again take out the maximum unsigned value. And let's just do the same arithmetic again. So that massive number as a plus 1. Sorry, plus 1. When I hit on calculation here, there we go. We didn't get any result back. We didn't get that 0 back. And if you look at the console here, we can see it says revert. The transaction has been reverted. That means an exception happened. And there we go. Happy days. That's great. But let's just see what actually happened. What caused this revert? Debug. And let's just step through. Now, if you just look at the instructions here, immediately what you're gonna notice is, imagine previously in an old version, well, in this version 6 of the Solidity, here we had push, following with a duplicate 4, and there was an add functionality. As you can see, there is no add anymore. So definitely something else is going on. So again, we look at instructions, top of the stack now is 0, and then the beautiful 64 times FFFFF is there, and duplicate 2. 1 is on top of the stack, duplicate all those Fs, top of the stack. Now there is no add. There's another thing, push to this thing. So what is that thing? That thing is effectively an address of another function that is now being called. Now we're going to go through a little bit of the rabbit hole here. I'm not going to go through all the instructions now, but effectively what happens is now there is an address of a function was put on top of the stack. So add didn't happen. Now from here on, you're going to go through those injected additional instructions that was put by Solidity to do a couple of things. The first thing it does is, I need to move it a little bit fast here. The first thing it does, it will find out the range of that data type. In this case is 256 unsigned, and it will find that and put that on top of the stack. And here we go. So if you now look at these instructions, push 32 FFFFF, this is effectively that range. And the other thing it does, it will subtract the second value, which is B, from that. And then it will do a comparison with, well, this is the second value. If that value is greater than, it will say, aha, this is going to result into overflow. I'm not going to let that happen. And we're going to go through reverts. Perfect. Nice. So things are solved in the compiler. Not really. Now, a few things happen here. If you remember, I talked about 22 edge cases that result into integer overflow. Out of those 22 edge cases, still overflow happen, even if you use the latest version of Solidity at this time is 8.10. When you do bitwise operation on any number, and or using any assignment or explicit or implicit coercion. So you kind of, from a 256 4-bit, you go to the 64-bit data type, is still overflow happen, and a compiler is not going to help you. The compiler only going to help you when we are just doing this basic arithmetic situation, like pluses, minuses, and multiply. So that is one thing to keep in mind. So still we need to be a educated, aware developer in that case. The other thing, and I like to point it out, is, and didn't mention it last time, is every transaction or request that happen on this Ethereum network or this blockchain network, it has a cost. It's like, when I run something, my computer has a cost of electricity and all the other things. And for these nodes to process our requests, they need to get paid off. Well, in some sense, they need to be compensated for that calculation that they do, because they're not just processing my request, they also do quite a few things known as mining to produce that response. So there need to be a compensation price for it. And this cost or this compensation that is being given to those nodes is known as a gas price. So this is a price that no matter what request you send to the network, that you need to be willing to pay for your request to be processed. Otherwise, nobody will not do it. Now, every time we do a transaction here, you can look at the transaction and find out what was that price, or effectively what was the gas price. And if you look at here, the gas price for a basic adding to number, it was this at the time when I executed that. So this is a cost applied regardless of whatever I want to do. And yeah, if the calculation is more complex, the gas price will go up. So just keep in mind this number. So it's 22,509. Now let's compare this. When I add the two number using an old version of the Solidity. So that contract that was used version 6 of the Solidity, and well, it didn't have the overflow check. But let's just see what is the gas price for that transaction. So I just executed that old code. And if I go to the gas price, is 2205073. So previously this third digit was 5. This is now 0. So almost around 25 or like 15 to 20% more kind of we need to do, or we need to pay, just because of that arithmetic check. Now, one thing I want to say, can we fix this problem in Solidity version 6? And again, we're still using the less gas prices. Yes, of course, yes. We can just put that condition of checking if let's say the result of A plus B is, if it is smaller, so this is like an if it is smaller than one of the values, this will effectively gives you us that range check for us. And I think I just went too much over the time, but you're gonna see here is that this one is actually cheaper than, so adding this check, compiling it with Solidity version 6 has a less gas price, and using a more modern version of the Solidity, which injects those preconditioning. So the moral of the story in this case was, by just adding your own check to Solidity, and if gas price is a thing, which is a lot of times, there's a lot of discussion around how we can do this transaction with the less gas price, will actually save you gas. So the more we know about security of this thing, the more we can save. So I'll just show you that the gas price for that number, again, add those two values, and we just compare that. And let's see, obviously it transaction reverted. So what is the gas price here? 2250. Okay. So with that, let me just jump back to my slide, just making sure if I have covered everything. And meanwhile, if you guys have any questions, please shoot. There we go. Okay, so yeah, we talked about 3 strategies: precondition check, upcasting, and dynamic allocated data type BigInt. That we don't have BigInt, so we're limited in these 2. So if you want to do precondition check, you do like one of the techniques is like that. So when you want to add 2 numbers, you have result, you add them 2, you check if the result is less than 1, and after that, happy days. Similarly, when it comes to assignment, we can do a similar check, just making sure the value is not beyond that smaller data type that we use. Well, that was all, and I hope there was something you could take out of this presentation. I don't have anything else. If you have any questions, please go ahead and pass over to Dan.
Alrighty. Thank you, Pedram. Let me just the scene. Right. Okay. Thanks for that. That was a very, very deep dive into the EVM.
Please.
Yeah, it's very interesting to see the good old days of C++ and C bugs coming back again to haunt.
Yeah, kind of happy but more sad, right?
Yeah. I mean, what's old is new again, right? It's a cycle,
Yeah.
and around we go. Thanks for that. I appreciate that. That was a lot to take in. First time seeing a lot of these things as well. It's like, wow, just wow. So there was I know we are over time, but there is the CTF. Yeah, do you want to show us how we can get started with that CTF and how all of that would work and the details of the CTF?
Yes, it's true. Just I saw one question came up on the chat.
Yep.
When we are executing Smart Contract to reflect the transaction, how would we know that the hash value has been reflected?
Yeah. If there's any questions, yeah, just drop them in the chat. Sorry, just
I don't
missed that.
necessarily know what do you mean by the hash value being reflected in the public blockchain. Like, effectively, what I started was if you can see pretty much the code, the contract codes. You can see all the transactions. You can see all the hashing that was done using whatever key that was used to do the signing, and all. There are actually networks that, as I said, is distributed. There are services online that you can even watch at the moment what is happening, like what transaction are being put at what transaction being reverted and all the other things. So again, from a security perspective, it's interesting because there are cases where, because it's a distributed network, effectively everything is being logged and can be monitored, and could be a different vendor come to you saying that, hey, we actually saw some attempts against your contract, because they can even see those transactions on the network and maybe they alert you because of that. So it's a kind of I found it quite fascinating, just from a hacker perspective. Yeah, so as you, Dan, said, let me just share perhaps my screen, talk about a little bit about the CTF part.
Yep.
And this
Back to you.
CTF will be open, as Dan mentioned, for another week. So please feel free to take your time. I would say this is the first time it's a AppSec, like the AppSec CTF. The goal of this CTF is to not just find the security vulnerability, but fixing it. And by fixing it, you effectively get a score. So if you have played the CTF before, it's not about exploitation here, it's about fixing the problem. Now, this was my dream, to encourage more and more people coming to the blue defensive side, helping us to fix the problem. Hence, during the whole pandemic situation, I put my heart and soul and my team to build an open platform, and this platform is effectively open to all of you guys to try it with a number of languages. It's a CTF style AppSec competition or challenges, where your goal is to fix security problem, and if you do so, you will get a score. The one that we have which is relevant to my workshop, so if you have tuned in, you can definitely solve a couple of challenges here. If you just head to play.secteam.com, I don't know where, I will let Dan and Gal to share that. Play.secteam.com, you just need to sign in. Once you signed in, head to this thing called dApp. I think the link for this is also on Meetup page. And we have picked 3 challenges for you to play around. At the moment, it's empty. A scoreboard is empty, so it's waiting for you to go and solve it. And everything is containerized. So these challenges are related to effectively this Solidity code that I just went through. It will, you just simply need to follow this 6 step here, or you can follow this local development setup here, and you can run it on your machine. Effectively, it's a Docker container that will spin up a local test network or a blockchain network on your host, and then there is a command you run following the instructions to compile it, run it, test it, and effectively you want to look at the content of there and try to find and fix the security issue. Now, for now, I will leave it as that. I'm online in the chat, and I will be also available throughout the next week if you have a stock or have any problem. So the goal is you go there, you fix the security issue, and anytime you are ready, you git, commit, push your code up. This will kick in some tests on our backend, and if you have successfully fixed the security issue, you're gonna see your name showing up here on the scoreboard. And I think we also have prizes for it. Is that right, Dan?
Yeah, I think
Whoever come first.
Yeah, I think you prepared a pretty awesome prize for the first to finish.
Yes.
Yeah.
So I've got a workshop, a defensive programming or defensive cloud native workshop coming up in October. Whoever wins this and become the first who solve the challenge will get a free seat on that workshop. So the challenge is on. I think that was all.
Yeah.
Is there anything else you want me to add?
No, I think that pretty much covers it. Let me just get back to this. I think like the CTF will be open until 5 p.m. the coming Wednesday. So that would be the 10th of August, 5 p.m. Melbourne time, because hey, we're Sydney time, AEST, because we are on that side of the world. So yeah, just hit us up. We'll go back online and make the necessary announcements. So looking forward to all the excitement. Definitely keen to try. I do have a question about the CTF though. So spinning up all of that, does that mean that I have to consume my own gas, or are we doing all this testing on a private blockchain?
So I lost the voice cut off. Sorry, what was the question?
So for the CTF, are we consuming real gas like actual ETH, or are we or is this on a private blockchain?
Beautiful question. Everything is mocked, and then in reality what happens is once you run that container, it will bring up a test network which is local to your machine in a single container. It will auto generate some accounts, and it will assign some fake 100, I think, ETH to each account. And then there are commands you can run, which is again in the instructions, make test, which will use one of those accounts to do some transactions. So you don't need to connect your real wallet or anything like that. All of them are kind of mocked and tested.
Yeah, sweet. Thank you. I appreciate that. Alrighty. I guess if there are any final questions, chat, if you'd like to chime in for any other questions. Otherwise, we will be hanging out in the Melbourne Chapter 8U Melt voice channel for a few more minutes until, I guess, 8 p.m. until the hour. Yep. Pedram?
Yes, I'm here.
Yep. So we'll hang out in the Discord. The link to the Discord, I'll put that up. It's in the description below the fold. You can head over to Discord. We'll be hanging out in the Chapter AU Melt voice channel. If you have any questions, hit us up there. Otherwise, I think we'll wrap up the live stream portion of this session. Thank you very much, Pedram. Really appreciate that deep dive and the insight into, well, integer overflow.
Thanks for having me, Dan.
Thanks for sharing. And thank you, everyone on stream, for coming, participating, and asking and engaging so much in chat. I appreciate it. And wherever you are, thank you and have a good day. See you in Discord.
Thank you.
Thank you.